Okay, we will start today's class. Today is October 4th of October. Last week we mainly covered the micromechanics or microscopical view of the composites. The reason we start with this micro view of the composite is that we like to understand the especially the carbon fibers, how small they are, and then toes and oven and the ply and etc. Of course, we're gonna proceed to understanding the mechanics, how to design, but we need to understand the microscopical view of the composite in manufacturing process and design process and selection of material. We always need to understand that at that point. One of the, let me, one of the interesting view of the woven composite is that I would like to share the this is a modeling procedure of the woven fabrics. Well, I don't mean to emphasize how to model that, but I like to show you the structures of woven fabrics. We have a warp and weft, 0 and 90, and you can see how they can be interlocked. And there are many different types. The most typical one is the plain whip, just a simple zigzag, and the twill whip. And you can see how to explain by word, but this is the kind of one of the woven fabric is called twill whip and then satin whip. So depending on how they are weaved, there is a special name for that. And now, when you see this kind of woven fabric, we need to understand the each color represent the toe, and toe consists of the 24K or 10K or 50K, depending on the toe size. So you can imagine how many carbon fiber can be there. Usually the woven fabrics is dry, can be dry or resin pre-pregnate. And if this is a dry, and then how the resin can be smeared or flow through this toe, and inside the toe there can be another flow. So we do have a computer modeling skill. This is just one example. Again, this can be modeled in the abacus using the Python. Please turn off your mic. Okay, and then what I like to show here is that the simulation using these models with all the wolf and webs. It's a simple plane weave, and this is the kind of let's say there can be some resin-rich area, and then this can be applied to a certain shear load or extension or biaxial load. This is very important in real structures of composites. Each toe can be straight or can be undulate because depending on these weaving patterns. And the smaller, the thinner and thinner, meaning that this toe has to be very much well spread. So depending on this pattern, I mean the real spreading, this can be the geometry or undulation will be determined. And as you can see, the effective stiffness will be 172 or 209, depending on this interlocked geometry. And this can be weaving pattern. Again, this is the all called the weaving patterns. And this is very typical in understanding winding pattern as well. In winding, depending on the poly number we chose, the final geometry will be like this. And then so it can be a twill or a plain twill or 8 hardness satin. And this is the effect of a weaving pattern on the forming process. Let's say this can be a dry fabric, and then we can drape. It's a forming process without no resin, or we can be resin impregnate. So during this class, please pay attention. So this is to demonstrate how this draping can be performed. As you can see, this is a time versus a displacement we can push. Let's say we have a sort of a mold, and then we can push, and as you can see, this is a real pictures together with the simulation. You can see how this can, the weaving woven can be deformed. And another important point is that, again, this depending on the plane and twill and the satin, let's say under simple extension, you can see the effective stress strain curve. Even though they are same toe, same composites, but depending on the interlocked, you can see the effective stress strain curve can be different. It's simply because of the effect of undulations. The most stiff structure will be a in this case twill 4x4, and this one shows like that. So as you can see, compared to others, there will be less undulation. And this is the one of the so let's say we have a woven and under tension, you can see how much the stress can be concentrated, and then how the composite can damage that. I mean, you don't need to fully understand all the behavior, but I just like to emphasize the effect of undulation in composites, not just in the woven, but also in many structures. Again, I like to emphasize the in the filament wound structures, this kind of can happen. So as you can see here, depending on this plain woven or basket woven, many different forms of the woven compared to real 090, as you can see, stiffness can be reduced by certain ratio, depending on, of course, the weaving pattern or undulations and the strength as well. And so but the failure strain can be larger and small, larger or very similar, because the failure strain is the amount of extension before the failure. So the failure strain in this case is this is the amount of a failure strain. So this failure strain can be even larger. But as you can see, the stiffness and strength can be decreased. This is all through a simulation, and you can see how powerful it can be. Even for the compression, stiffness and strength and failure strain compared to 090, others can be reduced. Also, you can notice that the strength between the tension and compression, these compression strengths can be smaller than tension. This is also a very important behavior of the composites. Okay, well, right now, what I like to emphasize is just the general review of the microscopical aspect of the composite, so that you can get familiar with the composite behaviors. And also last week, I wanted to emphasize the manufacturing process in composites, especially the we emphasize how this is just one toe. One toe can be spread, right? Can be spread, and it can be resin impregnate. This is my drawing last week. We start from the fiber and toe consists of the 20K or 40K. You can imagine how many fiber filament in there in one toe, and this toe can be weaved as a woven fabrics, and can be dry, and then plus resin, and just we demonstrate that how these the composites, I mean woven fabrics, can be stiffer and the weaker depending on the interlock. Again, the biggest advantage of this woven fabrics is that without the resin system, this can be a fabrics, right? Because they can be interact and they can be as a dry fabric. So we can layer these dry fabrics on mold, and then we can resin can be impregnate. Resin can be thermoset and thermoplastic. Now another one is that a tow can be spread, and not just one tow. One tow can be spread and can be resin. Thermoset and thermoplastic can be impregnate. Again, here one of the most important procedure is the spreading of the tow. There is air spray and some moisture spray and many mechanical vibration. So this one tow can be well spread, and then it can be as thin as the 0.1 to 5 millimeter. So this is the very important technology, followed by the resin impregnation. And to make the large pre-preg like the 1 meter wide, we can have many tows, and each one can be spread and into a wide pre-preg. So again, no matter what composite we are using, we need to understand how this one carbon fiber and tow, and then oven and the spreading and etc. And then followed by the manufacturing process. Now, I like to more demonstrate how these are made in the industry using some machines. We have some YouTube. Let me well, this is the one of the company. They produce some the machines. It conceptually looks like a very simple, just a spread and the resin. But in reality, the machine is not that simple. We have to do very multiple steps to make the well spread fibers. But this is the one of the final form of the production of a unidirectional carbon fiber reinforced thermoplastic tapes. Again, compared to here, this represent this process. We have a lot of tow, bobbin, and each from each we have a tow and spreading. And then here in between, very important process is called resin impregnate. So resin will be melt and then will be impregnated into a dry fabric. We can have a pre-preg, but this resin can be thermoplastic and thermoset. Well, the process will be quite different, but conceptually they can be very similar. So now in this case, the width will be about 1 meter. That is the standard, and this is the shows the thermoplastic tapes. This is the thermoplastic tape. It's gonna be very solid. Is a consolidate. It's not the thermoset. Thermoset, once it's a consolidate, we cannot melt them. But this is a thermoplastic. Thermoplastic means that once we have this tape, we can melt them. Well, this is the just okay. Here, actually, this is a starting point. As you can see, we have a lots of bobbin here, and starting from here, we have depending on the width and depending on the thickness. You know, last time while in your homework, you should be able to calculate how much the toe unit to make this certain width and thickness. Now each one will spread, as you can see here. Actually, the video goes reverse order. So basically, this is the toe, and then spreading. I will go this way. And spreading. This is a spreading stages. And then we can have a resin impregnate, and then we cut off two edges because there is not uniform. We cut off, and then we can have a consolidate. Is fully is a very thin composites, but this is the thermoplastic. Last week we emphasized the difference between the thermoplastic and thermoset, and then this is the edges. But this is the final form, and to make the very uniform property, again the spreading technology and the resin impregnation process will be very important. Okay, so you can have now. I hope that you have enough idea about the this thermoplastic impregnate procedure through toe spreading. This is the very similar procedures. Now here, I'd like to emphasize this is called each bobbin, and then its own tensioning system. Tensioning means that when you have a pull here, has to be reverse the torque so that this toe can be always under tension. Tensioning is very important to have a uniform quality of this toe plate. I mean the tree plate or toe plate. Now we have a comb, you know, so that it can be well spread. Well, and so that each we have a roller, many different roller. Each roller has this certain purpose, but as you can see, and we are spreading more and more, and through some stages. And this is a resin. This is the thermoplastic. Thermoplastic will be melted here on the top, and there can be some pellets or any form of the thermoplastic resin. Resin will be melted. As you can see here, this is a screw. I guess the screw goes this way. So depending on the thermoplastic, we will have a different temperature stage, like the 300 and 320, 350, and finally fully melts resin and go into actually the principle is not that difficult. We can produce our own this resin impregnate thermoplastic process. But this one shows the this is the not the carbon but the glass. As I was trying, I want to show the okay. This is the actually the thermoplastic resin. Input is just a pure resin we call pellet, and the you can imagine is like when you have a 3D printing, you will have a filament. That is, they are all thermoplastic as well, and then we can have a small piece is called a pellet. This pellet will be melted, and then well, I don't mean to go this much, but other important procedure is called thermoplastic composite. The rapid manufacturing of a tailored spar. Well, this is the spar for certain structures. As you can see, we have a complicated shape. And now, you know, these days, the airplane, the automotive, they are start to use the thermoplastic. One of the reasons is the thermoplastic is recyclable, and one of the most important point of the thermoplastic is the rapid manufacturing. Now you can see how they can be manufactured. See, procedure shows that pre-preg. Pre-preg is just the one we show that. Well, this doesn't have to be okay, this is a pre-preg or so resin pre-pregnate, which we just showed that, and then we layered depending on the layer we like to design. We layer, and then we have a stamping, forming, just press like the stamping. So using the toe preg, we layered as we wish, as we design, using the toe preg layered machine, automatic tape layering. So all the composite industry is moving toward this direction. This is the automatic manufacturing process of the composite structures. As you can see, we have a rotational axis, and then this plate is attached. And then this head is the toe preg layering, and then layered by, controlled by the robot system. So this is the key part of the design. You as a design, we design, and then as you can see, a lot of different angles. And now, well, of course, in this course, we will learn how to design of these structures, you know, the angles, and it looks like the plus minus 45, and there is a zero behind, and etc. So how we design to meet certain stiffness and structures, stiffness and strength of our structures. So we call local reinforcement. But now here, one of the most important point is that how this gonna be shaped. You will see that. Okay, this is the forming process. In metal, this is called the stamping procedures. Very, very typical procedures for the metal, but the composite is kind of challenging and but very much demanded in manufacturing of the composite. So virtual forming simulation means that we can simulate, starting from the layer, we simulate, and then how can be this deform, similar to undulations, and then consolidate. In composite curing process, we call consolidate, and thermoset, we call curing procedure. There are two different words. One is the consolidate, the other one is the curing. Curing is usually for the thermoset, and consolidate is usually for the thermoplastics. Now they are trying to emphasize the technology benefit of the thermoplastic, thermal forming, or just you can call it stamping. Tailored, what does it mean? Tailored layer. Tailored layer means that you, as a designer, you create your own layer. It's like you create your own materials. So improve the performance, and you can reduce the weight. And then near net shape layer, reduce the trimming scrap. Scrap means that you have to, certain part, edge part has to be cut off. But that can be cut off, scrap can be reduced. And shaping by stamping, flat, always a flat layer on simple tool. So you can lay up using the automatic tape layering machine. And then finally, you can have a very complex final geometry and consolidate by the stamping, high rate. High rate layer and the short consolidation cycle is the most important. Composite has to be, the limitation was the composite was mainly manufacturing process. It takes too long, and the manufacturing production rate was so slow because of a thermoset and some chemical reaction, and we have to use the autoclave, and we have to wait 8 hours and etc. But as you can see, the thermoplastic can be revolutionize the composite industry. And we can compete any materials like the metal or aluminum. Now those materials can be replaced by the composite, the carbons and the resin, and then you will see how this can be, how well can be extended to many different types of the composites. Now this one it's a combination with the this is the laminate. Well, this is just a simple pre-laminate. This is the thermoplastic, by the way. This one, we mostly we need a heat up this laminate. This is the thermoplastic. We need it to melting, and for like the 1 minute. And depending on the resin, it has to, temperature has to be above the 350. This is almost exactly same as the metal stamping procedures. Now, this is a very important manufacturing procedures. We inserted the flat plate with a certain shape. Now, during the consolidation, we can over injection. What does it mean, over injection? We can inject some plastic. We can inject some plastic to have these very complicated structures. So this rib, let's just call the rib, or some reinforced structures can be overmold, just a one piece with the main structures. And this structure can be so strong, grid stipple panels. And a lot of structures, as I mentioned, using the thermoplastic can be now how not just by the automatic tape layering, we can just cut by hand or by the CNC machine, and then we can just layer. But this is the very much conventional old technology of a layer by hand. But these days is all automated by the robot and tape layering machines. So preforming means that since it is okay, sorry, this is not the thermoplastic. Okay, this is the thermoset pre-preg, and we need a stage called preforming. Preforming is the, we have a forming procedures. So this is not cured yet. This is just a forming procedures, okay, layer to layer and so on. And then followed by the full curing process. This is the thermoset. And this can be a very quick, it's called PCM, pre-preg compression molding. Very similar to thermoplastic stamping procedures. This is the video from the Hanguk Carbon. Hanguk Carbon is famous for producing pre-preg. You know, they own a thermoset pre-preg, and they are trying to demonstrate how the composite can be manufactured using pre-preg compression molding. Okay, so you need a cutting and you need to have a stamping. That's why they use the hand layer, you know, the resin thermoset. You can use the automatic tape layering machine, but this usually starting start with a wide prepreg. So you cut it manually and then layer and put it into a mold. And you can see there is a heater there, and then press, and then curing. So this is a PCM, very famous manufacturing procedures of the thermoset. Okay, well, in here, the thermoplastic, one of the very typical procedures of the process is this is the thermoplastic winding, and we have a long the pipe, just a plastic. You can imagine this is a kind of a liner, is a continuous, and then outside this is a thermoplastic tape or toe pad. And this is the typical procedures. You can see this tape is tapes are wound over the well, this is a pipe, as you can see, and this is the feeder, I mean the roller. This is like the protrusion, is a pull. Okay, and you can imagine how the composite can be made of. And this is the composite with the 3D printings. 3D printing can be large, like this. You have a base composite, and then you can have a 3D printed, very complicated structures over the composites. So so resin or short fiber reinforced plastic can be melt and then 3D printed over the structures. You know, the 3D printing, the biggest advantage is that, you know, this is an additive manufacturing. Additive means that we are adding material rather than cutting away the material. So we can save a lot of materials, but the composite manufacturing procedure is usually has been additive by such as layering and such as the filament winding. These are all the additive manufacturing procedures. Now the 3D printing is certainly one of the typical additive manufacturing procedures. Okay, well, the purpose of this introduction is to help you to understand in general about the composite procedures and manufacturing. And as you did in a homework, there can be a lot of different way of manufacturing of the composites. And you can have your own procedures. Why not? You can have a hand layup. You can have develop your own machine, and depending on the application. So you don't have to limit. But in doing so, very important point is the understanding of fibers. Okay, understanding all the can be short, can be long, can be very continuous, or can be interlocked like the woven, or sometimes stitched. Stitched means that, you know, woven, as you can see, have a interlocked to be to make the form, but just without interlock, we can one just the direction. They can be a form of a fabric by stitching, and it can be a pre-preg. Again, we don't have an interlocked, we don't have a stitchy, it just have a resin impregnate, so it can be a form of a sheet. You know, it's not complicated procedures. So all these procedures, you can have a laminate, you can have a composite, then it can be applied to many different structures for the aircraft and automotive, and even for the battery, you know, the enclosure, and many things. But again, like to emphasize the how each fiber will play its own role in composites, and together with the resin system. That is the all the composite behavior are coming from, and the tensile behavior and compressive behavior, transverse and in-plane and impact resistance, and etc. Now we, as a designer of composites, how can we design structures with the understanding of all these composite things? Again, composite, through a composite, the structure can be very light. Okay, structure can be very light, and the structures can be, of course, the manufacturing process can be automatic, and structure can be very light, and then structure can be recycled. You know, all futuristic features can be incorporated by designer. So you, as a designer, you need to understand the manufacturing procedure, and you need to understand the mechanics of the composites, understanding of a fiber, understanding of the resin, and understanding of the interface. You know, this color represent the interface, which will represent the bonding between the fiber and resin system. So no matter what your major or application, understanding of composite will help you or enhance your career as a designer. So understanding of composite is just not the specific application. Understanding of composite is the you know, really broaden your career. Well, this is the another manufacturing procedures.
Over 30 years, automated dynamics
This one is a very, you can imagine that
performance automation equipment
is the automatic, as I mentioned.
Our team of technical sales engineers works closely with every countries. We are committed to taking performance
and as you can see, all kinds of a shape. Now, manufacturing procedure has to be up to you. Understanding of the
thermoplastic and thermoset tapes, with particular expertise in situ consolidation of thermoplastics. All of our manufacturing equipment includes sophisticated proprietary software and simple, user-friendly mechanical systems. We also provide every client with on-site training, ongoing expert support, as well as tailored service packages. Our market-leading fiber placement technology is used. Here, again, this is the tape comes here, and then you tape here, right? And then you need to heat up the tape. Well, this is the very hot heating device. You just melt and then you press. So always the chemical procedures is controlled by the press and heat. Those are two factors. And thermoplastic doesn't need a complicated chemical procedures. Thermoset, you need a weight, you need another factor, time. Time is a very critical component in thermoset. Why? Because we have to wait for chemical bonding procedures like the but the thermoplastic, all you need is just a press and heat. To design and manufacture continuous fiber composite structures. These solutions, which replace metal, reduce weight, isolate electronics, or offer high-level corrosion resistance, offer performance unequaled by metals for conventionally molded components. A wide variety of shapes and sizes are available, including cylinders, cones, box beams, I-beams, triangles, coils, flat laminates, ovals, and complex geometries. If you have a very demanding problem requiring advanced composite materials, our engineering services can help. We can assist you in training, concepting, prototyping, testing, and production scale-up, even for complex problems that seem impossible. Our roots in engineering go back over 30 years to the founding of our company. Automated Dynamics takes performance and composites to a higher level by empowering the world to conceptualize, manufacture. So the composite over 30 years, Automated Dynamics has specialized in the manufacture of advanced composite structures, high-performance automation equipment, and solutions-based engineering services. Our team of technical sales engineers works closely with every client to develop and deliver strong, lightweight structures and industry-leading processing equipment that can withstand the work. And this can be another application. I mean, the application of composite is unlimited. Since it can be very light, you know, the weight can be very important feature. Composite robot arm, it can be applied to robot arms. It can be applied to sorry, it's not the quite proper slide. Anyhow, we just review some of the manufacturing procedures of the some of the composite labels. We studied from this slide. You know, I was trying to, you know, we just reviewed of the understanding, not fully, but the fiber size and resin, and between them there is some interface bonding, and so this is the ply, and you can imagine. Don't just look at the consider as a one. Material. It is the composite. So it is better to visualize how many fibers in there, and then toes and wovens. Okay, we are trying to review from here to there. So it's a micro level, or is sometimes called meso level. Okay, so now we are trying to move to main structures of a laminate. And then main structures. So no matter what structure, we can think of these structures, or airplane, or aircraft, or pressure vessels and anything. And then you can imagine there's a laminate. And then each one you have a woven or ply, and then a fiber and so on. Again, I just want to emphasize one thing. If the airplane usually used to be made of the aluminum. Now, if it is aluminum, can you change material property like a Young's modulus, 70 gigapascal? No, we cannot. All we can change is the shape. But composite, as you can see, you change the angle inside, you change the fiber resin system and hybridize them, meaning that you can create your own material. How wonderful it can be. You just create your own material, and not only the geometry, but also all the material in there, your own materials. And then depending on the structure's requirements. So you need to understand what the requirement is, like how much force and temperature, and then understanding of this. Now you as a designer, you make the shape and the layout sequence and etc. And then you can be a very strong engineer in design of composites. So I cannot emphasize enough how important, how strong you can be as a designer of the materials. I don't want to say just the composite material. Designer as a materials. No matter what structure, we always use the material and design, right? So anyhow, so we wanted to review of the composites behavior and characteristics. Okay, well, let's have a 10-minute break. It is 4:02. Let's get back to 4:12. Okay. Well, we right now we like to more understanding of all the composite behavior. I mean the manufacturing procedure. We need to understand the manufacturing procedures from the bottom of the micro levels. Very important procedures. I'd like to share some of the slides. We already went through this one. Now I hope that you can now better understand. You know, I think most of this procedure is kind of new to you. So sometimes I repeatedly show and emphasize the same slide, but now it is a PCM. Now you understand what it means, a pre-preg compression molding. So this woven can be a resin impregnate thermoset, and then you press, and you can see how this toe can be rotated and how can be void can be generated. I mean, detailed shape and some angle rotation can be simulated or can be measured through manufacturing procedures. But now you can imagine or visualize how this can be this kind of can happen. This visualization or this understanding is the important
once you understand what can be the procedures, and then you can go into more in detail by your own simulation or by own manufacturing procedures. Now, another important manufacturing procedure is like the infusion procedures. Infusion, you have a dry fabrics and then a resin will flow rather than resin impregnate. Okay, this is a process, resin flow. Again, resin flow is not like the resin impregnate. We have a dry fabric. Dry fabric can be stitched or can be woven, anything. And then we have make this some foam. But very important point in here is that to understand how resin will flow in certain direction. Because the resin will flow under a certain vacuum or pressure. So, there is a simplification saying that, I'm not trying to complicate you with a certain equations. Okay, I like to minimize the equation, but this is the important to understand. Okay, so Q is like the flow rate. Flow rate means that the resin will flow. Flow means that we have a certain direction with a speed, like the resin flow speed, how water can flow, how resin can flow. And there is a subscript I, means that it has a vector with a certain direction. Now this resin flow will depending on the pressure. We can have a different pressure. Like the certain area, it can be a vacuum, and also this is a vector. Now, depending on how they flow, there are relations. This resin flow rate, and this is the pressure head. There is the coefficient called K. K is the permeability, permeations. So permeation, we need to understand these permeations to better predict how the resin flow. So this is a special machine, but this machine is nothing but just the let the resin flow, and then using the camera, we measure how the resin flow. So it's not a special machine, but imagine that this is a dry fabric, and then we apply a certain pressure on the left hand and right, and then what will happen? Well, the resin, since it's a liquid, resin will flow like the flow with a certain speed and certain direction. In this case, it's just one direction, just resin flow, and it will take time, T1, T2, T3, how much it can flow. So from this test, we can see the speed of the resin flow. So this is, again, is called permeability. This permeability is this is just a purely one directional permeability. So relate to a previous one, like we can see that this is the 1 kxx. So certain flow rate and certain pressure, we have a resin flow. But imagine there can be many different coefficients depending on the pressure, depending on how the resin flow. So now measurement of this permeability is important. So we let the resin flow from, and we have a camera system, and then pressure pumping here, and then resin will flow. There's a resin source there, but resin flow in this direction and that direction. So it just spread and spread and spread. So this flow can be measured by the two radius, R1 and R2, and then speed. So
this is the sort of well, there could be some analytical procedures, and there's a nonlinear equation of the anisotropic permeability. Anisotropic, why we call anisotropic? Well, if this is a fully circle, then it's going to be isotropic permeation flow. But depending on the layer, the resin will flow in certain direction, fast, certain direction, slow. Imagine the fiber is arranged this way. The resin will flow very fast in this direction, but the slow in transfers to a fiber. So you can imagine that why this can be anisotropic. Anisotropic means that, back to this equation again, we have this formula. So depending on this pressure head, we can have a qx, x directional velocity, and y directional velocity, two different coefficients. So and this is the sort of equation. And again, this flow can be measured over time using the camera. So we can measure that. Now, 3D permeability is that the resin can flow not just in the plane direction, but through the thickness direction. This is the cross section. And then a resin can, the dry fabric can be very thick. So resin can flow not just in the plane direction, but also through the thickness. So in this case, we have a z-directional permeability, permeations. So the let's say we have a different resin flow composite with a different, and you can imagine how can we calculate the permeation through the thickness. Again, I'm not trying to explain the how the equation derived, but the more important point is that how we understand the behavior of the manufacturing procedures is like the resin flow. And there are several important relations between the permeability and the fiber volume fraction. Let's say fiber volume fraction is low, then permeability, in other words, how fast it can flow. It can be very fast. And then if fiber volume fraction is high, the resin can flow slowly, right? And microscopically, again, the fiber can, resin can flow in this direction, and resin can flow transverse direction. There are several research and derivation of the equation showing that relation between the fiber volume fraction and the resin permeability. Okay, you can always find these equations. We have a through the thickness effect, and also we can develop a Excel tools, and now we have a different layups with a different permeability with a certain direction. Now we have a many layers, and how can we calculate overall permeability? This is the we can have solve this equation, and this can be developed Excel. So again, this is the flow front line. Let's say again, starting from here, resin can flow in this direction, that direction, and over the time, 10 seconds, 20 seconds, and 30 seconds with a certain layer. Now you can see that by measuring this circle to radius over the time, we can measure the permeability. Now, with the permeability, we can simulate, all kinds of resin flow, like the when you make the manufacturing. Sorry, this is not the same one. So for this kind of permeation or resin flow for the resin transfer molding or infusion procedures, this procedure can be also analyzed with the micromechanics. For example, this we have one fiber and resin system. Now you can imagine how many, this is a toe, and toe, how many fiber can be in there. And then depending on this undulation, you can imagine how resin can flow. With the understanding of the 1 micro, as you can see here, it shows the resin flow. And it can show the how the resin flow in the longitudinal direction and transverse direction. Now we have this one fiber, and now one toe consists of 24,000 of a fiber. And now you can understand how the resin flow. This is all through the simulation, our simulation. And using the this is the and with this simulation, we can measure, we can estimate the resin, how the resin can flow in the oven and many different types of ovens. How can they flow? So the point I like to emphasize is that when you manufacture the composite, you don't just look at the macroscopic view, but always try to visualize what can be what's going on inside the structures. Okay, that is a very important view. Okay, so the reason I'm showing you this is the we have demonstrate of the clamping or draping and compression, but that is the resin impregnate, right? Resin impregnate, but this is the resin flow. So you can imagine the how the resin can flow. And then curing or consolidation, and then you can make the many different types of composites. So there is a very famous composite tools. It's called the process simulation tools. It's a composite usually called a PEM RTM, and then once RTM through these procedures, the resin can flow. And then it cured. It cured means that it can have chemical reactions, and it can predict distortions and forming. Forming is the one we just discussed, like the pre-pregnate forming. But the RTM is the dry fabric and resin flow. And then either way, forming or RTM, or infusions, the composite can be distorted through a chemical reaction of a resin or thermal stress. And now this can be applied to let's say automotive. Okay, automotive. This is the simulation. This is the composite side. Automotive, we have A pillar, B pillar, and C pillar. Usually we make this whole part is a one piece. How do we make the one piece? Well, each one we have a preforming, and then we have a big mold. We layer to layer, and then once we have a dry fabrics layered, and then we use the resin transfer molding or infusions. So this is a draping analysis. I mean, same procedure as the before. And then, yeah, this is the, yeah, it's called a cabin. But as you can see, each part can be have a different preforming, and then into one big piece. And between each preform, we have a little bit of a interface, but that can be okay. And then once we have the structure, so we can have a natural frequency, we can have a buckling behavior, we can have a you know, as a structural behavior. So we need to understand the structural behavior, such as the natural frequency and buckling, and also large deformation and stress and strain, etc. And again, this is the one types of preforming procedures. Okay, well, it's supposed to show some deformation, but this is the final form. And then resin can, depending on the where the resin is supplied. Here is a resin inlet, and you can see how the resin can go in and go out. So through a resin flow simulation, you can understand where the resin go in, and the resin can, the air pressure will go out, so that every part, inlet and outlet, is a filling time. We can perfectly design of the manufacturing procedures with the understanding of a resin flow. And to do so, we have to understand the permeation we just reviewed. This is the, and then finally, we need to understand that the final form can have a residual deformation, because the all the composite procedures will go through shrinkages caused by the consolidation or curing procedures or thermal stresses inside these structures. So this can be, understanding of this is very important. So when you make the mold or design of a mold, we have to understand this thermal residual deformation. And we consider this residual deformation. That's how we design a mold. No matter what mold we design, we need to understand this residual deformation. It's an important concept, and so another interesting manufacturing procedures will be like the this is the now you understand how the UD preg tape can be made of. This is the thermoset, and then we chop them. We have a chopped pre-preg, not small one, but 50 millimeter by the 8 millimeter. So understanding we have a resin already there, so we have a kind of a in roll, and then we just cut a certain part, and then we press them. We can have a sort of structures. So this is a very much random behavior, but we can imagine, we can simulate how this can be like this one is the random short chopped pre-preg and randomized, and then we throw a mold. But here we have a resin is already there. So this is the kind of a design, but very importantly, this the toe, chopped toe or chopped pre-preg cannot be uniform, cannot be same all the time, but is a probabilistic behavior. So understanding or simulation of this kind of behavior will be very important. And now these things really apply to manufacture of the window frame for the airplane. This is the draping of a window frame. And also can be applied to, this is the PCM, prepreg compression molding. You can see how the part can be made up. But the most important point or feature of this chopped prepreg is that this complexity. You can see how complex the structure can be. We cannot, it's very difficult to make the structures with one prepreg, continuous fiber. So we have a chopped and then enable us to make the very complicated structures. Okay, well, another very interesting behavior is the composite impact behavior of a composites. The reason this is nothing to do with manufacturing procedures, but I like you to share with these procedures for you to better understand the behavior of the composite microscopically. So let's say we have a scale plate with a center. We have a impact vertically, and then we just analyze the quarter plate with all symmetry. So this understanding of a composite impact behavior is the well, so important and still going on. So depending on the layup sequence and depending on the woven fabrics, and now you can imagine we have each fiber in there. And the global behavior is of course a result of a local fiber and resin behavior. And depending on the layup angles, well, in this case, 0, 90 and 0, 93 and symmetric. You can imagine that, you know, each toe will have how many fibers in there. So microscopical understanding, all the simulation, you can imagine how much the time or how much complexity can be involved in this behavior. While nothing is impossible in simulation, so we can model with a fiber and resin and like this, and then you can see how this fiber can be broken under impact, and you can imagine how this damage will propagate. And then this is the each layer to layer, we call separation between the layer is called delamination. Delamination. So fiber, the weakness can be from delamination between the lamina to lamina or ply to ply. So prediction of this kind of a delamination is very, very important. And as you can see, it's never been done in composite society, but we are able to predict this delamination shape by modeling microscopical aspect. We hope to publish this one, but we didn't do that yet. But anyhow, as you can see how this can be impact and how can be damaging, propagated so quickly, and the fiber can be broken here. I'm not saying this is the real exactly same behavior, but the
I guess there's some video procedure will, okay, well, as you can see that, you know, the through this impact, this is a center view, quarter view, and then you can see how this impactor can go through, penetrate into composites. And this kind of behavior of composites are so important. In the aerospace structures, the structure can be subject to this kind of impact. And then structure can be very weak, especially under compression. So it's called compression after impact, CAI, compression after impact. So understanding of impact behavior is very critical in design of composites. And the so here the study was that, you know, we can have a very thin ply or thick ply. Now you can see how we can make the thin ply or thick ply is depending on the how we spread the toe. If we spread the toe very well, we can have a thinner, we can have a thicker. So, but now layup, same amount of the 0.90, but the different thickness. You know, the 0.90, 0.90, thin, 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 but the 0.90 thick. Total thickness will be different. The same, but the number of layers is can be you know, the thin and thick. So, well, this is just a one attempt to simulate this kind of behavior, helping us to understand the composite and helping us to design of structures eventually. And also, this is the all possible through, I mean, this is just a demonstration. It's not possible to simulate this way. I mean, it's a really crazy procedures. On the modeling all the toe, I mean, the fiber. So it takes the several you know, days to simulate that one. While we can be crazy sometimes, but anyhow, but in reality, we can simulate some special methodology. It's called a micromechanics of a failure, the failure procedures, failure theory. We will study more about the failure theory, but let's say we have a toe and woven and under certain objects, and then impact. Now we like to understand how this structure can be damaged, like the wind turbine blade, like the aircraft, like the automotive, even for the pressure vessel. All we have a bullet, and then we like to understand them, understand the behavior of this kind of formulations. Now these structures woven can be a braiding. Braiding, difference between the braiding and woven is that braiding, you can have a many different angle. You know, the zero, I mean the plus minus, there are like a 30 degree, but the woven always 0.90, but braiding, you can have a plus minus any angles. So this is the braiding. So braiding is known as the very strong for the impact. And you can see that how we model the older braiding, but again, each one represent one toe. So you as a programmer or designer, you can generate these kind of patterns. Well, this is the real, it's not the photo, this is the real generation of the geometry,
using the Python in Abacus. So you can program with the one unit cell, one unit module, and you can generate it this way and that way. It was done 2014 in our lab. So about 10 years ago, we start to model and all the micro meso as a pioneer. Nowadays, a lot of composite research center follow, and they also do a micromechanical modeling and then understanding and so on. So we are very proud of our pioneering of the composites in our center. So anyhow, impact simulation of a braided composite, like the older braiding, again, can be 25, 45, and 60. And again, the woven, okay, woven can be only 0, 90. But the braiding, you can have a many angle depending on the weaving. So all the mechanical property of a fiber, resin system, and the fiber volume fraction, and depending on the thermoplastic and the thermoset, the penetrations with a different velocity can be simulated. I'm not just trying to emphasize the simulation, but we as a designer need to able to visualize thermoset and thermoplastic and top and bottom. And as you can see, you can go through, and this is all braiding, by the way. You can, this is a very high speed impactor, or you can imagine this is a bullet. Like the the bullet-proof jacket for the soldiers. They are wearing this kind of a protecting jacket, or can be structures of the aircraft, or can be structures for the pressure vessel, hydrogen tank under the bullets. These can be we can simulate. And this is the purely simulations. And you can see, if you as a designer and then as a programmer as well, this is all program using the Abacus with the macro language, script, Python. And there's no limitation for you to, as a designer of composite. And you can make yourself very unique designer of composite. With all this kind of simulation behavior, and then now you see the CAI, compression after impact. Compression after impact, so important behavior of the composites, like the structures, where inside we can have a comb and the impact, and then you can have a damage. Now this damage structure will be subject to a compression, and then how the strength, compressive strength, can be degraded under this impact. This is the most important characteristics of the composite for the aircraft. When you design, you have to go through and this procedure and test. So far, there's no standard methodology or prediction of this CAI. Very luckily, or very proudly, we are the first one to simulate this CAI simulation. What make us the possible? While mostly understanding of a micromechanical behavior of composites. So as you can see, we can do many things, different layup sequence, different thermoset and thermoplastic and resin system, and then now impact, there will be a resistance of the impact depending on the layout and fiber and resin system. And then you can see a lot of different simulation behavior. Well, this is the same same thing as we just watched, but this is a thermoplastic and thermoset. And then this is a top view, and there will be a backside, and you can see how this can be a damage can be generated, or strain can be generated. And then this is the compression followed by the impact. As you can see, the compression behavior will be significantly dropped due to a damage generated by the impact behavior. So this is the another, okay, the topic I'm trying to share with you is not the main topics of this course, but I like to help you to understand the composite behavior from a micromechanical view. So the now this is an open hole tension of thin and thick. Thin means the thin ply or thick ply. This is the problem statement, like the specimen. Open hole, there is a small open hole. This is the tension specimen. There's a small open hole, a 1/4 inch the diameter, and this is open hole tension. And then on the tension, now we try to understand what will happen to here. So the now the study was that the effect of the layer thickness, the thin layer and thick layer. Now you understand how we make the thin layer or thick, thin ply or thick ply by all matter of the spreading toe. And then the understanding, this is the experimental observation of open hole tension. The thin and thick is quite different failure mode. The thin is almost vertical, and thick is the like the plus minus 45. Of course, this is the 0 cosine 0, 90 plus minus 45 behavior. This study was done when was it? It's about the 8 or 10 years ago. At that time, we composite society didn't understand why there is a failure like this or failure like that. And then through see this one thin, we have many specimen. Very consistently, we can observe that there's a very thin vertical failure, and this is a thick ply failure. And then there's a clear observation. Now there's some physical reason there. So thin, this is a thin, we call brittle, very brittle behavior. And the thick has a very complicated behavior. So there is a reason for that. Now we are all able to understand by the simulation. It's a complicated procedure. I don't want to go through that. But as you can see, all through a micromechanical failure analysis, we understand how this can be a plus minus 45 failure, and then this one, it can be a very brittle, a 90-degree failure. So the we can see how this damage can propagate. This is called damage propagations. Well, this is done using the abacus, but abacus doesn't have a feature of the MMF, and we had to implement this scheme and technology. And then we can understand, and now this is a microscopical, more detailed view, and under tension, and you can see how this damage can propagate through the vertical. This is, I'm sorry, this is thick, like the zigzag, a little bit of a zigzag view. And you can see this is the many layers, 0 plasma 45 symmetric A layers. This is the A layer, this is a microscopical, the local view. As you can see how this damage can generate and propagate. We already know that the under open hole, under tension, here and there is the stress is a much concentrate, and that behavior can be well simulated by this analysis. And now this is a kind of a thin, looks similar, but the we have a more ply, like the 7 times. And then, as you can see, just the almost a vertical failure mode. And well, as you can see, how this damage will generate here, and then propagate vertically in case of a thin ply. So this is a pretty much advanced the mechanics of a composite. We cannot cover everything in one course, but I just, we as a designer need to understand macroscopically, also microscopically. Again, if you are able to do this simulation and were able to explain, then you can be a very competitive designer. There was a physical understanding and explanation, and all things. Trying to show you what we can do, what we can happen in the micromechanical behavior of the composites. This is a field hole tension. Field hole tension means that, okay, many composite structures, especially for the aerospace, there is a fixed hole and fixed bearing, and then this composite can be subject to a tension like that. So on the top here, there, okay, sorry, yeah, there's a bottom here, because sorry, this is the some rigid pin inside, and the pin is pushing upward. So the top can be, this is a vertical view, and as you can see, each ply can crash. Very complicated. Imagine each toe and each fiber, how complicated it can be. So depending on things, and this is a simulation, and this is the older simulation. Well, we cannot predict the exactly same, but we can catch what can happen. And this is a thin and thick, and this is the kind of simulation. And here is the bearing load and then pushing. And you can see how tall, how ply, and how fibers can crash. Very complicated procedures. So the there can be many different the design procedures. We as a designer, I don't mean to complicate you, but the behavior of composite can be very complicated. But more important point is that we can we need to understand the general behavior of the composites depending on the laminate. I didn't share this slide, but after class I'm gonna select some slide and then share with you. so that you can well remember. But more important point is that all the class is a video tape and then upload to YouTube. So you can study or review any times. Okay, well, we need to go through all the mechanics of the laminate. In here, any case, as you can see, we have a laminate of the each ply with the different angles. Well, again, this thing is very complicated depending on the ply thickness and the layout sequence, resin and fiber, and etc. But in this class, what we like to mainly cover is to understand the laminate. Laminate is like just a simple geometry, a layout, and then some special applications. That is what we're gonna cover in this course. I'm sorry, I don't give you a chance to for your questions, but if you have a question, feel free to leave a question in Katalog and also chatting window. We can just Google it. Let's say impact compression after impact, say a composite, how important it can be. And then you know, when we design the this is all the compression test, but the design of an aircraft is a very typical procedures. Like here, you have an impact, and then you damage it, and then compression. So in any aircraft manufacturer, they do this kind of research, or try to understand them, and even you know, simulating crack in modern well, these composites. And this seems to be exactly same as we did, like the hole, and then this is not the impact, but this is the impact under. We already have a damage there. Impact, right? And then compression, as you can see the damage line here, right? So the reason why this CAI, compression after impact, is important, aircraft is a certain subject to some impact. So the upper skin can be damaged. Now this is under bending, upper skin will be subject to a compression because of a bending. Now, how much the impact, how much the bending, or how much the compression can be overcome in composite. That's why the Boeing, Airbus, Embraer, and also NASA, they do a lot of study to understand this kind of behavior. So still a lot of research is going on. And whenever they develop the new carbon fibers, and new fiber, new resin system, they always do these types of studying and experiment. And you can understand how fibers can crash and toss by understanding interaction between the resin and carbon things. well, don't try to attempt to simulate, okay? It's not possible, but understanding of this oil behavior can be very critical. This reminds me of the some machining with a tool like a drill, machining of the composite things. This is also very, very important research area that, you know, we have a certain laminate with a certain layout. We like to make a hole. We make the drill, and then we have a how can we drill depending on the layout and then our resin system. This is also important behavior of the composites. Well, this one is the like the fan blade. You know, the all the engine has the aircraft has engines, and then this engine fan blade is all made of the carbon composites. This is the so important application of a composite. This composite fan blade, engine blade, revolutionized the aerospace, the aircraft technology. So strong in on impact, so light and so powerful. I hope we can demonstrate impact. Let's try to impact fan blade, aircraft, engines. Okay, this is the one of the blade. Okay, this is the one of the blade, and then you can see it's a impactor impact the fan blade, and this can be a bird strike. You know, the bird, you know, the flying bird. It's the biggest problem is the bird impact on the fan blade. So it causes really a big catastrophic failure of the airplane. So the sometimes it causes the huge damage of the impact. And this fan blade, you know, consists of 100 of different layup sequence. That's pretty much know-how. You know, the Rolls-Royce, they have a very, really wonderful fan blade. And this fan blade is all made of composite things. While this is the worst case, this aircraft engine blade damages. Not just for the, well, this is not the composite, but this is the gas turbine engine. This blade also can be made of the composite. And Boeing 737, you know, this all, let's try to, I hope we have some simulation. But simulation is, you know, we not try to just simulate, but just the better understand the all the behavior. Well, simulation is almost it is possible, but with a very fast, you know, the explicit simulations like that, you know, the impactor and then damage and breakdown, and then the whole blade will be unbalanced and vibration, and then how structure can be safe, and etc. So this is the old composites, and then there will be some impactor. impactor or some one of the fan blade can be just the dropped off, and then this is the simulation of a containment. You know, the protector outside is called a containment, and this containment is so important to protect all failure. So this containment is also composite materials, and the yes, this containment. I'd like to say. Well, okay. Well, just fan blade containment. Oops. Sorry. Fan blades containment impact. You know, I'm trying to tell you that this containment outside, this one, the outside, is also made of a composite. It's a braiding composite. Why braid? As I briefly mentioned, that this one is a braiding structure is so strong under impact. So even one of the fan blade is broken or damaged, and this containment is strong enough to protect them. So the I don't know what it is. Okay, no, not this one. So that's how the braiding composite developed at the very beginning to protect this engine fan blade. This is the braided composites. So anyhow, the well, I cannot cover all the application of a composite, but I just like to give you some idea of the how this composite can be applied, how can be simulated, how specific we can think of. You know, like the bird strike. You see this one, bird strike. Like the well, this is a papers discussing evaluating impact damage of a flat composite plate. It's just a flat composite for surrogate bird strike testing. So the all the problem statement, then it can have a bird strike. Well, I don't want to go through this one. Another one is the bullet test of high pressure tank composites. You know, all the fiber reinforced composite for the CNG or hydrogen. This one of the very important behavior is the bullet proof, or not the proof, but bullet penetration behavior, and the well, especially in United States, they are allowed to carry the guns. So in United States, they have a very special test to get the certification of a bullet penetration test. So you can imagine trying to find some good example, but okay, they call gunshot. This is the gunshot. Do you see that? This is a 700 bar. It's so high pressure, and then there is a gunshot. You just fire with a gun, and then you can see this the bullet will penetrate, and then we can see how this hydrogen tank behave. Well, it doesn't burst. But this is a high-speed camera, like a 30,000 frame per sec. And I saw some test for the bullets. But this one is just the Toyota. This is their hydrogen tank. And the United States, again, United States, they have to demonstrate to this kind of a bullet, hydrogen tank gunshot. This is just a test. Well, speaking of the pressure vessel, there are many different ways of modeling. Modeling means we first need to
Toyota Safety Sense, TSS, is a suite of active safety technologies and advanced driver assistance systems. Toyota Safety Sense 3.0 introduces a number of enhancements over the previous generation, including an upgraded forward-facing camera with higher resolution and wider angles.
Usually design means that the shape, that's what they mean, usually conventionally mean by the design, but composite is not just for the shape, but also all the material inside. And as you can see that ANSYS can be used, the ANSYS is analysis tool and can be well used to model the geometry and then material properties and simulate all the structural and the high pressure behavior and assigning all the material property and etc. Well, it doesn't show much, but this like to emphasize that how we can use the conventional commercialized tool like the ANSYS and Abacus can be used to model the geometry and the material property and etc. There are many tools, or you can develop your own to model the filament-owned structures.
We will be investigating the iterative design and analysis of a compressed hydrogen fuel tank. As the demand for hydrogen vehicles grow for either commercial or domestic use, the need to reduce mass and improve gravimetric efficiency is essential. When designing and analysing a composite pressure vessel, we usually begin using P-con shell elements. The thickness, material, and fibre angle can be changed rapidly, enabling the design team to quickly iterate in concepts and research the effect of certain parameters. In this sensitivity study, we are looking at how changing the fire branding affects the deformation and sizing failure criteria of the pressure vessel. Observations like these can contribute to a laminate optimization study, as well as being compared with previous videos.
Well, this gives you just a short overview of the pressure vessel made of the composite layers. But this view can be not just for the pressure vessel, can be for any structures of a composite. You know, the composite can be thick and thin, and then how do we model? It can be as a shell, can be a 3D, and etc. It's same for the pressure vessel, same for the other structures.
Once a laminate conjunctive has been selected, we can use solid laminate decomp elements to investigate the through thickness or interlaminate stresses. This is an essential step for thick-walled composite structures such as pressure vessels or nests, where thin laminate assumptions no longer apply and large through thickness stresses can be observed under loading. However, this stage can be time-consuming and computationally intensive. Therefore, through the use of decomp shell elements of synthesized layups demonstrated in the previous video, significant time and money can be saved in the design and optimization process. To further optimize complex structures, we have developed novel scripting abilities to map automated winding paths and laminate manufacturing information into our analysis tools. This allows us to maintain accurate file directions through shell and solid models, thus providing greater certainty in areas of complex geometry, such as pressure vessel end caps or structures that require post-winding machining. We also work closely with material suppliers to enable us to accurately model bespoke laminates with materials information, including interlaminate properties. This is especially important when modeling extreme environments, such as high temperatures or marshland environments, or when designing thick laminate components. By analyzing the components using accurate winding paths and material data, through engineering, we provide greater certainty for customers looking to invest in novel manufacturing methods or materials, with the time and cost of developing and testing prototypes greatly reduced. Thank you for watching, and be sure to check out Fluor Engineering's other.
Here, we can see here in design of any structures using any material, we have a step. We have to understand the material behavior, you know, like the tension or like the compression or any material behavior. And then depending on the application, we have to understand manufacturing procedures. And we have to understand the requirement, how much pressure in there, how much, you know, the temperature and etc. So the, it applies to any composite structures. For those who better understanding of a composite, there are so many YouTube and then analysis procedures and etc. There is one very important tool. It's called wound sim.
These are deactivating points in the cylinder.
I don't mean to go through all the procedure right now, but the wound sim is the or WCM is can be used the all the geometry, and geometry means that, you know, the thickness change, and then along with the thickness change, the layup sequence will be different. So the material property and geometry are coupled in this case. This is very interesting, very important view. Material property and geometry, they are coupled, not separated. That's why the design of a composite pressure vessel make it very complicated. Well, very complicated means it's a good story for composite designer. Why? Because a conventional designer cannot design the composite structures. So complication of a design procedure of composite is good for those who are the composite designer. Okay, you can make yourself a very competitive and a very unique engineer. But anyhow, well, I just want to from here to there to cover all. I didn't cover everything, but the composite starting from a microscopical view, we can do lots of applications, and also design and manufacturing and the procedures. So okay, I just want to close. What is it? I'd like to close today's lecture by emphasizing that time to time, I like to go through how the composite can be applied to real structures like this battery enclosure. So many things, especially for the automotive. But with the understanding of all the manufacturing procedures, but I like to emphasize the one very important point is that, I'm sorry, I'm trying to find the slide. It's not easy to find one slide out of hundreds of but we have to find it. Oh, by the way, the composite understanding of composite can be also applied to electronics. Like the folded your cellular phone. It is the glass of the your cellular phone actually is the composite full of layered is a OLED. There's many different layer and layer and layer. Now this can be folded. How can we fold it? There can be a lot of electronics in there, and then with understanding all the lamination, we can better predict the foldable display. This foldable. This research was done in our lab more than 6 years ago, but understanding of the folded is a very important features. And 3D printing, like the all kinds of structures now can be 3D printed. And even automotive main structure can be fully printed. And the 3D printing is together with optimization, especially for topology optimization. We can shape that, very complicated. Now complexity is not a problem in 3D printing of the composites. And these things is huge printing with the 3D layers. And this is also understanding of a micromechanical view and aspect of the composites. Well, the one I'm trying to find is very similar to this slide. Well, we already went through this one, but again, the point I like to emphasize again, similar. We need to understand materials. Okay, now you can better understand what I meant by this, material and design and manufacturing. Materials can be, fiber can be a carbon and heavy tow and etc. Resin can be thermoset and thermoplastic and all kinds of understanding of materials, raw material, I would say. And design means that depending on the layup sequence and the winding patterns and and understanding of the structural behavior like the buckling and natural frequency and etc. And also manufacturing procedures like the resin impregnate, resin flow, or the winding procedure, or 3D printing, and the PCM. We understand these three concepts. Then you will be super composite designers. So you can create your own scheme of the design procedures, and you can be that scheme can last forever in your whole life. So again, in this class, I really would like to welcome all of you to a composite society, and then depending whatever application you are planning, like the big container or big aircraft or robots or automotive, whatever designer as a mechanical engineer, if you use the composites, understanding all this behavior, well, you can be again very unique designer, like not just for the general structure, but also for the electronics, the wearable device. These are all layered, and we need to understand the layered behavior. And then so, okay, well, that I'd like to close today's lecture by, again, the general introduction of the composite manufacturing and with understanding of a micromechanical view and so on. So again, this lecture will be saved and then uploaded to YouTube. And importantly, you need to keep visualizing what will happen in composite and for any kind of structures. Okay, well, this is the I'd like to close our today's class. We hope to cover. We will cover the mechanics of lamination of composites from our next class. Okay, thank you, and see you next week. And then I will share with you through Katalog and YouTube all the class or topics we covered. Thank you so much, and bye. Well, there was well, I can discuss later. Well, shortly, the thick layer, thin layer, there's a pros and cons. Okay, pros and cons. Thin doesn't mean always good, and thick can be better in terms of structural behavior and in terms of manufacturing procedure as well. Okay, sorry for late reply. Bye.
감사합니다.